Previous lecture, we have studied the relation in between the elements of the triangle, and for this we define the sine rule and the cosine rule. These two rules are very interesting and these two are very important. Okay, now in today's lecture we go with our new rule related with the elements of the triangle and is here projection rule. Okay, to define the projection rule, we consider triangle ABC. In triangle ABC, we consider your length of the sides are A, B and C. Okay, and here angles are angle A, angle B and angle C. So related with these elements, we have a relation here. In first, A is equal to B cos C, then plus C cos B. This is the first relation for this projection rule or for the elements of the triangle. Then second is here B is equal to A cos C plus here C into cos A. Okay, and in last here in third we consider C is equal to here A cos B plus B cos A. So these three relation is for projection rule and for the elements of the triangle. Here again remember here small ABC are for length of the sides and here capital A, capital B and capital C are for angles of the triangle. So in today's lecture where we see this projection rule. Okay, let us prove first case for this projection rule. Okay, here we prove A is equal to B cos C plus C cos B. Okay, here I write in triangle ABC, prove that here first case is A is equal to cos C plus B cos C plus C cos B. We have to prove this relation. Okay, let's go with our proof. Okay, so here we consider all the possible cases related with the angle B and for angle C. Okay, we have to consider various cases. In first case, we consider your angle B and angle C are acute. Then for next case, we consider your angle B is obtuse and we consider angle C is obtuse. Then for last, we consider here B is right angle and we consider here C is right angle. We have to consider all these possible cases. Okay, so here we go with our first case. In that we consider B and C are acute angles. Okay, so in case first we consider B and C are acute angles. Okay, and to define this case, we consider one triangle. In that we consider B and C are acute. Okay, so we draw one figure for this case. Okay, we consider this triangle. This triangle is here A, B, C. Let us consider the sides of the triangle. Here side opposite to the angle A, we consider this as A. That is length of this side BC is A. Then length of the side opposite to the angle B is here small b. then length of the side opposite to the angle C is AB, and here length is small c. Okay, to define this relation, to define this first relation, we draw altitude from this point A on BC, which is meet at D. Okay, so from A we draw altitude that is perpendicular on BC like this. Okay, and in BC our new point is D. Okay, we consider here right angle is at D. Okay, now by using our definitions of trigonometric functions, here we have to prove or we have to define cosines of B and cosines of angle C. Let's define cosine of B, that is cos B. Here in the triangle ADB, here in the triangle ADB, here cos B is equal to, everyone knows, to define the cosine, we consider the adjacent side and the hypotenuse. Okay, here adjacent side is BD. This divided by, here hypotenuse is having length C, so this divided by C. So we get here BD is equal to here C cos B, we get this relation. Similarly, for this cos C, we consider triangle ADC, and in that cos C is, here again we consider adjacent side upon hypotenuse. Here adjacent side is DC, okay, and here hypotenuse is B, so DC upon B. And here lastly we get DC is equal to B cos C. So we get BD as C cos B and DC as B cos C. Now in this figure, everyone knows here BC is BD plus DC. Here I write in figure, okay, here BC is equal to A, or we consider, okay, here BC is equal to A, and this is equal to here BD plus DC. Now remember here BD is called projection of this AB on BC, and this DC is called projection of AC on BC. Okay, so here BC is equal to A and is equal to BD plus DC in this figure. Okay, this is equal to, we know BD is here C cos B plus here DC is B cos C. So we get our relation here A is equal to C cos B plus B cos C. So we prove here our first case by using here B and C are acute angles. Okay, let's go with our next case to prove this relation. Here we consider B is obtuse. We consider only B and we consider B is obtuse. Okay, so in case second, we consider B is obtuse. B is obtuse. Okay, and to define again this relation, we consider one triangle in that B is obtuse. Okay, so here in the figure we consider triangle ABC, and in that B is obtuse. Okay, so this is our triangle A, B, C. Here B is obtuse angle. B is having angle more than 90 degree. Okay, then we consider one perpendicular on BC like this externally. Okay, so this is meet on point D, meet in point D. Now here again, remember here projection of AB on BC is DB, and your projection of AC on BC is DC. Is DC. So we consider here DB and DC only. I repeat again, here we consider projection of AB on BC as DB, and here we consider projection of AC on BC is here DC. So we consider DB and DC only to prove this relation. Okay, so here in triangle ADB, here in triangle ADB, we consider cos B. Here again, we know here in triangle ADB, B is acute. So here cos B is having adjacent side upon hypotenuse. Here again, remember length of the side. Here length of the side opposite to the angle A is small a. Then length of the side opposite to the angle B is here small b. Then here length of the side opposite to the angle C is small c. Okay, so here cos B is having dB upon hypotenuse. Here for hypotenuse we consider C. Okay, therefore here dB is equal to C cos B. Now we define cos C, since in our case we have a cos C. Okay, so we define cos C here. Here cos C is equal to define cos C, we consider triangle ADC, and in that here cos C is having adjacent side DC upon hypotenuse is B. Okay, therefore here DC is equal to B cos C. So we get this dB and we get this DC. Now by using this dB and DC, we define our relation. Okay, here we consider this figure again. In this figure, we know here DC, or we consider this BC as, we consider BC. Here BC is is having length A, and in LHS we have a length A. Okay, so BC is equal to A and is equal to, we know here BC is DC upon DB. Okay, DC minus DB. This is equal to, here DC is what? We know DC is B cos C. Now here remember one thing, here cos B is given. Here actually this B is having measure more than 90 degree. Okay, if this is more than 90 degree and we want here acute angle, here we want acute angle, here we consider C cos pi minus B. Let's correct this case, here C into cos of pi minus B. Okay, so here for DC we consider B cos C, then with minus sign. Okay, here we have dB. dB is having C cos of pi minus B. This is equal to here B cos C as it is with minus sign. Now everyone knows here cos of pi minus B is minus cos B. Okay, so here C as it is, inside the bracket minus cos B. And in last we get here B cos C plus C cos B. So here A is equal to this one. So we prove this relation by using our case, here B is obtuse. By using the case B is obtuse. Very simple case it is. Okay, now we go with our third case. In that we consider here B is having measure of 90 degree, that is B is right angle. Okay, case 3, In that we consider B is a right angle. B is right angle. That is having measure of 90 degree. And to prove our case, we consider right angle triangle. Okay, this is our triangle ABC. Here again we consider the length of the side. Okay, here side opposite to the angle A is having length A, side opposite to the angle B is small b, and length of the side opposite to the angle C is small c. Now here remember, here D is coincides with B. We have to draw the perpendicular drawn from the point A on the BC. In first case we consider this perpendicular. Okay, here again we consider the perpendicular drawn from this point A on B. That is, here B and D are coincides with each other. These two are coincides. Okay, now we consider this triangle to define our case. Here we consider RHS of the given statement. Here in RHS given, here C cos B plus B cos C. Okay, now this is equal to here C cos B. Okay, here everyone knows B is having measure of 90 degree. B is right angle. If B is right angle, here C cos B is 0. Here C cos B is 0. Everyone knows cos B, that is cos of 90 degree. We know cos of 90 degree is 0. So C cos B is 0. Okay, here in next B cos C as it is. Now in this triangle, we know B cos C is BC. Here B cos C is BC. Okay, so BC, and we know here length of BC is A. Length of BC is A, and this is our LHS. Okay, so in this case we prove here A is equal to C cos B plus B cos C. Okay, so in these three cases we consider various cases. I repeat, in the case first we consider B and C are acute angles. Then in a second case we consider here B is obtuse. Then in third case we consider B is right angle. Okay, similarly for C is obtuse, we can prove for C is obtuse, and we can prove for C is right angle. So in all other cases, in all the possible cases, we prove this type of relation. Hence here we get A is equal to C cos B plus B cos C. So this is for our projection rule. We consider only our first case, we prove our first case. Similarly, we can prove another two cases. So, very interesting part it is, and very important part this is projection rule. So in today's lecture we cover our rule and is projection rule. Okay, in previous lecture we consider sine rule and cosine rule. Let's repeat these two rules again. Firstly we see sine rule. Okay, to define the sine rule we consider triangle ABC. In triangle ABC we consider the important relation in between the elements of the triangle, and is here A upon sine A is equal to B upon sine B is equal to C upon sine C and is equal to twice R, where R is the circumradius of the given triangle ABC. Then we see second relation. We consider this as cosine rule. Cosine rule. Here again, to define the cosine rule, we consider triangle ABC. In triangle ABC, okay, we consider first case. Here A square is equal to B square plus C square minus twice BC into cos A is the first one. Then second, here B square is equal to A square plus C square minus here twice AC into cos B. Then in third case, we consider C square. C square is equal to A square plus B square minus twice AB into cos C. This is for the cosine rule. And in this lecture, we consider projection rule. Here in third, projection rule. Again, to define the projection rule, we consider triangle ABC. In triangle ABC, again we have three relations. In first, we consider here A is equal to B cos C plus C cos B. Then second, we consider B is equal to here A cos C plus C cos A. And for third, we consider here C is equal to A cos B plus B cos A. So, in these three rules, we consider the relation in between the elements of the triangle. Let us consider some examples related with these rules. Okay, example, let's go with first one. In triangle ABC, if measure of angle A is 45 degree, then angle B is equal to 60 degree, then find the ratio of its sides. The ratio of its sides. Okay, we have to find ratio of its sides. Means we have to consider the length of the sides firstly. Okay, here in the triangle ABC, we consider length of the sides as here A, B and C. We have to find ratio in between A, B and C. So we find this relation or this ratio by using our sine rule. Okay, so here we consider sine rule by sine rule. Here again I write sine rule, our sine rule. A upon sine A is equal to B upon sine B is equal to C upon sine C and is equal to twice R. Okay, here in first two, we consider first two. Okay, here I write this as A upon B is equal to sine A upon sine B, and we consider next two. Okay, second and third. Here by using second and third, I write B upon C is equal to sine B upon sine C. This is by using our sine rule. Okay, then here I write this as here A adds to B adds to C is equal to here sine A adds to sine B adds to sine C. So by using this relation, by using this ratio, we find A as to B as to C. Let us consider this as 1. Okay. Now, here we have to find sine A, sine B, sine C to find this ratio. Okay. Now, for this, we know, here for this, we know angle A, we know angle A, angle B, and we have to find angle C. Now, everyone knows in triangle ABC, some of the angles is of 90 degree. Okay. So, we consider the relation here A plus B plus C, and we know this is of 180 degree. Okay, here we know A is having measure here 45 degree plus B is having measure here 60 degree plus C as it is, then this is equal to 180 degree. Okay, he is having 180 degree. Therefore, here we know 45 plus 60 is 105. So 105 degree plus C is equal to 180 degree. And lastly, here we get C. Here C is equal to 75 degree. So here C is having measure and is of 75 degree. Now we know A, we know B, we know C. Let's find sine A, sine B and sine C to find this ratio. Okay. Here sine A is equal to sine of, we know A is having measure 45 degree. So sine of 45 degree is equal to, we know sine 45 degree is here 1 upon root 2. Next, we find sine B is equal to, here sine B is equal to sine of 60 degree. We know sine 60 degree is here root 3 by 2. Here is root 3 by 2. Okay. And in last, we consider sine C. Also, here sine C is equal to sine of 75 degree. We have to find sine 75 degree. Okay. So by using the compound angle, that is, here I write the 75 degree as 45 degree plus 30 degree. Now everyone knows the sine of 45 degree plus 30 degree is in the form here sine of A plus B. Okay. We consider another letter sine C plus D. Okay. We know sine C plus D is sine C cos D plus cos C sine D. Okay. By using this formula, here I write this as sine of 45 degree into cos of 30 degree plus cos of 45 degree into sine of 30 degree. Okay. Now this is equal to, we know sine 45 degree is 1 upon root 2. Okay. Then we know cos of 30 degree. Here cos of 30 degree is root 3 by 2. Okay. Here is root 3 by 2. Then plus cos of 45 degree is 1 upon root 2 into, here sine 30 degree is 1 upon 2. Okay. And lastly, here we get root 3 plus 1 upon 2 root 2. Now we know sine A, sine B and we know sine C. Okay. So by using 1, from 1, here A as to B as to C is equal to, we know sine A is 1 upon root 2. Here I write 1 upon root 2. As to, here sine B, we know sine B is root 3 by 2. Then we know here sine C is root 3 plus 1 upon 2 root 2. Okay. And lastly, here we get 2 as 2, 2 as 2. Okay. So here we get this relation, we get this ratio. Okay. So by using sine rule, by using the sine rule, here we consider we find this ratio. Okay, let us consider another example. Second example, in triangle ABC, prove that relation is given, sine of B minus C upon 2 is equal to, here B minus C upon A, B minus C upon A into here cos of A by 2, cos of A by 2. Okay. Now we have to prove this relation. Okay. Here again, by using the sine rule, we prove this relation. We consider our sine rule. By sine rule, our rule is having A upon sine A is equal to B upon sine B is equal to C upon sine C and is equal to K, where K is constant. Okay, here I write A separately as, let's equate, or we consider first and this last K, we get A as K sine A. Okay, then here B is, again we equate the second with last K, we get K sine B. In last, here C is equal to, we equate this third with last, we get C is equal to K sine C. Okay, now we know ABC. Let us consider RHS. Okay, here RHS is equal to, RHS is having B minus C upon A into your cos of A by 2. Okay, let's replace A, B and C. Here this is equal to, we know B is K sine B, we replace B by using K sine B minus, small c is having K sine C, here K sine C, this divided by, we know A is having K sine A into, in next cos of A by 2 as it is. We keep this as it is. Now here from numerator we here K is we consider K as common. Okay, so here this RHS is equal to, okay, here K is common, inside the bracket sine B minus sine C, this divided by, in denominator K sine A into cos of A by 2. Now here K and K cancel, here only remains sine B minus sine C. Now we know sine B minus sine C. Here sine B minus sine C is 2 cos of B plus C upon 2 into sine of B minus C upon 2. This is formula for sine B minus sine C. This divided by, now here sine A is given. We have to write this sine A in the form of A by 2, since here in next A by 2 is given. So I write sine A as 2 sine A by 2 into cos of A by 2. In next, cos of A by 2 as it is. Now here cos of A by 2, cos of A by 2 cancel. Here only remains, again here 2 and 2 cancel. Here remains cos of B plus C upon 2 into sine of B minus C upon 2, and this whole divided by sine of A by 2 only. Okay. Now here we want only sine of B minus C by 2. Here already we have sine of B minus C by 2. Okay. Now here B plus C by 2 is given. We have to consider, we have to focus on only cos of B plus C by 2 and sine of A by 2 only. So here, okay, we consider one relation. Everyone knows here if A by 2 plus B by 2 plus C by 2, we know this is pi by 2. Here we want b plus c by 2. Okay, so I write here b plus c by 2 as pi by 2 minus a by 2. We replace this b plus c by 2 by using pi by 2 minus a by 2. Okay, so here cos of pi by 2 minus a by 2. We replace b plus c by 2 by using pi by 2 minus a by 2. In next, here sine of b minus c by 2 upon sine of a by 2 as it is. Okay, now here this is equal to, we know cos of pi by 2 minus a by 2 is sine a by 2. Is sine a by 2. Everyone knows cos of pi by 2 minus theta is sine theta. So here cos of pi by 2 minus a by 2 is sine of a by 2. Here in next sine of b minus c by 2 as it is. This divided by sine of a by 2. Now here sine of a by 2, sine of a by 2 cancel, and here only remains here sine of b minus c by 2, and this is our here LHS. This is our LHS. So by using RHS we find LHS, and by using our sine rule. So in today's lecture we see one important rule, one important relation in between the elements of the triangle, and we define this as projection rule, and we see two important examples related with the sine rule. In next lecture we see some more important examples related with this rule. Thank you.